So thanks for attending my session. I'm Xiaohong Gong from open source software team. I'm currently working on OpenJDK, mainly focused on the Graal compiler optimizations and the enhancement for the AArch64 platform. So here I will give you a talk about our optimizations on the AArch64 backend. So before it, I will give you a brief overview of the Graal compiler. And then I will talk about Graal optimization status before our optimizations. And then I will mainly talk about our optimizations. And finally, I will have a talk about our future work. So what is Graal? Graal is a compiler. It is written in Java language. It can compile the Java bytecode to the machine code. Currently, it supports three backend: x86, AArch64, and Spark. The Graal compiler can be used as a JIT compiler. Also, it can be used as an AOT compiler. As a JIT compiler, it can be a replacement for the C2 compiler of HotSpot. And the C2 compiler is the server compiler in the OpenJDK HotSpot. And as a AOT compiler, Graal can be also either used as a HotSpot AOT compiler. Also, it can be used as a substrate VM. We usually call it a native image. So this is the Graal architecture and its relationship with the HotSpot. Graal is the compiler to generate assembly code. So the HotSpot is the virtual machine to give the runtime support. It contains the garbage collection, class loading, garbage collection, and interpreter compiler, and the client compiler and the server compiler. We usually call it C1 and C2 compiler. So Graal is VM independent, so that means it doesn't know anything about the HotSpot VM. It can only communicate with the HotSpot by the JVM compiler interface, which is first released in JDK 9. Another important framework is the Java framework. Java is a language implementation framework that it uses Graal as the custom compilation. Because this is not in scope of my topic, so I will not give you the detail. This is compilation framework. At the beginning, Graal will get your bytecodes and class informations like metadata from HotSpot. Then Graal can begin its compilation with the Java bytecode parser. It will pass the Java bytecodes to its high-level nodes. Then Graal will apply some high-level optimizations to it. Then before the backend start, Graal will load the high-level nodes to low-level nodes. The low-level nodes are platform-specific. Then, together with some low-level optimizations like instruction selection, then register location and code generation. After code generation, Graal will transform its compilation results back to the HotSpot. And this is all the compilation results containing the target code, assembly codes, and some informations like reference map, mesh and call informations, and the exception informations, and source mapping. So why we will choose Graal? A main key feature of the Graal compiler is that it is written in Java language, which means it has high development efficiency. It is more easier for the new compiler beginners. And then Java is safety. It has exception while not crashes. It has no dangerous pointers. And then Java is more maintainable and extendable. It has good ID support for debuggers such as IntelliJ ID and Eclipse. So besides the language features, Graal compiler also has its own features compared to the LLVM and C2. So first, Graal is designed for the speculative optimizations and de-optimizations. All the metadata for the optimization is propagated through all the optimization phases. And then Graal it is designed for exact garbage collection. It can create all the read and write barriers before and after object allocation, new object, and it will build object pointer maps for garbage collection. And then Graal has many aggressive high-level optimizations. All these optimizations are applied to the high-level nodes. It can use the control flow informations, also can be applied multiple times, like partial escape analysis. And then Graal is modular architecture, unlike compared to the C2 compiler. So it's more easier for the developers to add or remove your own optimization phases. And it is VM independent. So if you did some modification to the compiler, you don't need to compile the hotspot together. And finally, because Graal is written in Java language, so it can compile and optimize itself. This is also a good optimization opportunity. So next, I will talk about optimization status before our optimizations. This is optimization comparison with the C2 compiler. For the middle end part, middle end optimizations are applied on the high-level nodes, which is public for all platforms. So most of the optimizations are similar with C2, but in advantage, Graal uses partial escape analysis, while C2 uses full escape analysis. Also, Graal can catch more virtual function machines. That means Graal can inline more methods. So all these two optimizations can largely narrow the performance gap with the C2 compiler. So, in shortage, some optimizations in the middle end still have some issues that need to improve. Also, for the auto vectorization part, currently it doesn't support on the AArch64. So in future, we will take some time to enable it. So for a backend is optimizations for each backend, for each platform. So for our AArch64, no instruction selection and intrinsics are added before our optimizations. So this is our main work. Also, the Graal uses linear scan register location, while C2 uses graph coloring. Here is the performance comparison about of the spec GBB benchmark compared to the C2 compiler. As we can say, the performance is almost the same with the C2 compiler. So as a conclusion, compared to the C2 compiler, Graal is new, and even without much backend optimization on AArch64, it still has a similar performance with C2 for some cases. But Graal is still missing a lot of optimizations and OpenJDK new features. And its performance for some cases is still worse than C2. So we need to catch up with it. So I think with more optimizations added for the AArch64, the Graal's performance will be compelling in future. So here I will mainly talk about our work on the AArch64. During the past 1 year, we mainly focused on the backend optimizations on AArch64. Like we add several match rules to delete or use the let instructions, like mnag, tbz or cbz. Also did some optimizations for the did some array-related optimizations, like just reshaping and memory bulk zeroing for initialization. Also, did some optimizations for intrinsic part, like bitCount, and other optimizations like memory burial. For the middle end, we also did some optimizations, like we add an integer divisor and a reminder phase to optimize it when the divisor is a constant, to reduce the instruction strings. Also, we did an optimization to the if statement to reduce the jump instruction. So next, I will give you several examples of our optimizations. This is an optimization for the if elimination. So this is Java example max. Initially, Graal will generate a compile instruction and a conditional jump instruction to implement it. After our optimization, sorry. After our optimization, we can use a conditional selector instruction to remove the jump instruction, because the jump can largely influence the performance. This is the example for the just reshaping. This is a memory out of a Java library or Java array. It always begins with a header part with 60 bytes, and then is the element one by one. So if you want to load or store and remember, you must firstly multiply its array index with its type size, and then add the header offset. So before our optimization, Graal will generate these 4 instructions. So after our optimization, we can use and add extended instruction and load the immediate instruction to implement it. We can reduce 2 instructions. This is optimization for the bitCount. Before our optimization, many instructions can be generated. And after the optimization, we use 4 same instruction can implement it. So this is a performance comparison for the GMH benchmark. GMH is a Java Harness benchmark, micro benchmark. The result is lower is better. The blue part is the results that with our optimizations, and the gray part is without our optimization. So as we can see, it more or less has some improvements. Also for the algorithm part, currently has 7 to 130% improvement. So this is the performance results for the vector part, because we have some array-related optimizations. So the improvement, we still have some improvements here. About 0 to 6 to 51% improvements. And this is the performance result with the intrinsic part, because we did some intrinsics for the bitCount or min-max. So so the improvement, so here it has a large improvement, mainly for the bitCount and the min-max. So it has 7 to 326 improvement. This is our performance comparison with the decouple benchmark, because it is a complex application, so the improvement is not so huge, but but still we can say with our optimizations, it still has some improvement here. So next, I will talk about our future work. In future, we will still continue doing the backend optimizations on AArch64, add all the missing match rules and the intrinsics. Also, in the middle end, there are still some optimizations like loop related. It still has some issues to be improved. Also, some ARM architecture new features like SVE and auto acceleration is not spotted yet. So we will also spend some time to take a look at it. Also, there are some issues for the register location, like stack splitting. So we will also take a look at it. Okay, that's all from my today's session. So, any questions?